Okay, we'll get started. So I have a problem today, and the problem is I want to charge two electric vehicles. I have two electric vehicles at home. I want to charge them. I'm seeing prices at every 15 minutes interval. So every 15 minutes, the price for electricity would change. So I'm not sure how much you are aware of the electricity market, but at the wholesale level, so at the university level, university is probably paying different prices for every 15 minutes. So from 12:30 to 12:45, university is paying one price for electricity. At 12:45, the prices are going to change. Okay, and certainly university knows what the prices are going to be, but in most of the situations, there is some fluctuation in that prices that the university sees over a 24-hour period. So let's consider that problem, but a simplified problem so that we all can understand and relate to. So I have a car, I have two cars. I want to charge the two vehicles, and I want to formulate this as an optimization problem. Okay, so what is the problem? I want to minimize cost of charging. What are the constraints in this problem? So I have two vehicles. My price for electricity is changing over 24-hour period. So the cost of charging would be summation of cost at time t multiplied by the demand at time t. Okay. But what are the constraints? What do you think is the constraint? Yes.
Does it depend on like how much electricity like a car battery can store?
Yes. Perfect. So charging rate. Charging rate for every car should be less than equal to some threshold. This is the maximum amount of charge that the car can hold at a given time. Typically speaking, the charging rate is a function of the state of charge of the vehicle. But let's assume that we are in a simplified setting, so the charging rate is below certain threshold for each car. So these thresholds would depend on the car. So I may have a truck, and I may have a SUV, and I may have a small passenger car. And in all these three cases, the threshold for how much we can charge every minute or every hour or every 15 minutes interval would be quite different. Anything else? Okay, sum of demand of every car should be equal to the demand of the total demand at time t. Anything else that comes to your mind? Yes.
Does it depend on like the type of car itself?
That's included here, right? So the type of car, the charging rate is different for different car. Anything else that you think is different for different car? How about the total demand from each car? Right? So my car is charged at 50%, your car is charged at 25%, his car is charged at 90%. So each car has different state of charge. So summation of demand of car T should be less than equal to, I would say, the 1 minus state of charge of the car, or rather times the battery capacity. So somebody's state of charge is 90%, somebody's state of charge is 10%, and depending on that, the total demand has to be this. And by the way, The demand cannot be negative. We are not assuming that the car is charging so my car is charging the university. I'm assuming that university charger is charging my car. So the demand has to be greater than equal to 0. In fact, each demand of car T should be greater than equal to 0. Not just the sum, but the total. But at each point of time, the demand has to be greater than equal to 0. Okay, there could be some other constraints too, but let's not worry about other constraints. So for instance, you could have a total constraint on the total demand. So you have a single parking structure and there are 10 chargers in the parking structure, and there is only a 200 ampere line that goes into the parking structure. So it cannot have demand of 400 amperes because the line is constrained by 200 ampere. So you could have some constraint on the total demand because you don't have enough capacity in the electrical panel to be able to charge all the vehicles. What do you notice here? What we notice here is I'm trying to minimize a function such that h of x equals to 0 and g of x is less than equal to 0. So I have an equality constraint here and I have a whole bunch of inequality constraints here. So today we are going to solve this problem. I mean, we are not going to solve it, but we are going to come up with necessary and sufficient conditions for optimality. Sorry?
What are the decision variables?
The demand for each car. This is the decision variable. How much will you charge each car at every point of time? That's the decision variable. This is x or xi. Okay, so x is a very high dimensional vector and this is xi, and that's what we are trying to optimize. By the way, this is not a random problem. One of my PhD students graduated solving this particular problem, and we solved this problem for Ford Motor Company, where they wanted to aggregate all the Ford vehicles, where this whole demand was actually met by renewable energy. So it was constrained by the amount of renewable energy getting generated, and we had millions of decision variables. So the innovation there, the reason why he got a PhD was because this problem was extremely high dimensional problem, and we came up with a way to solve this particular problem. He's now working at Ford trying to commercialize this technology. So anyways, it's not a random problem, it's actually a real problem. So this real problem essentially maps to something like this. You have f function from Rn to R. You have h function from Rn to Rm, and you have g function of Rn to Rr. Now, of course, in most situations, I mean, there was a time when n was equal to 2 and m was equal to 1 and so on. Nowadays, if you go to industry and you're trying to solve this problem, you're trying to solve some problem for Walmart or Amazon or Nvidia or whatever, typically n is of the order of 10,000 to 10 million. M would be of the order of 100, 200, something along those lines. And this R could be of the order of 1 million to, I don't know, 5 million, 10 million, and so on. Okay, so it's very complicated. So nowadays the problems are extremely complicated, and these kinds of problems are appearing in logistics company. And if anybody of you want to get a job in logistics company, do let me know. Send me your resume. I'll refer you. But these kind of problems appear in logistics companies where you are trying to optimize the routing of the truck, or you're trying to figure out which truck should go to where at what point of time, carrying what kind of load. So that's a hot topic right now. A lot of people are trying to solve that problem. They are trying to solve this problem in startups, not necessarily in university. And of course, there are problems that appears in electricity markets. People are trying to solve this problem, and I'm sure there are many other situations where people are trying to solve the problem that I may not be aware of. Okay, any questions so far? Wonderful. I want to minimize f of x, h of x equals to 0, g of x less than equal to 0. Okay. What's the notion of regular point here? Oh, before regular point, I have to talk about active constraints. We did talk about active constraints before, right? For manifolds of optimization. Okay. So maybe not a new topic. So we have a of x is j in 1 to r such that gj of x is equal to 0. Yes.
Is that A of X or?
Yeah, this is A. This is script A. Yeah. Do you know LaTeX? You use LaTeX? No? Okay. This would be Math Cal A in LaTeX or Math SCR A in LaTeX. Okay. So this is A of x, which is the set of all indices such that gj of x is equal to 0. And the regular point the definition is x is regular if and only if gradient of h1 of x, gradient of hm of x, gradient of gj of x, j in A of x are linearly independent. Okay, so what is the regularity? So we have, of course, the usual thing where all the equality constraints, you take the derivative with respect to x, they have to be linearly independent. But now I'm adding to the same set of equality constraints all the active constraints as well. And then I'm asking this entire set to be a set of linearly independent vectors. So let's say I have n equals to 1000, m equals to 100, and the set of active constraints, the size is 200. So there are 200 such indices where gj of x is equal to 0. Then this is 300 vectors. And we need to make sure that these 300 vectors are linearly independent at x. Okay. How do you check for linear independence of 300 vectors? Anyone knows? Yeah.
They can determine it if it's not.
Okay, so this is the matrix would be 300 cross 1000, or no, 1000 cross 300, because you have this, each of these gradients is in Rn, and n is 1000. Yes, yes. Okay, so I'm sure you have studied it in linear algebra class, but just go back and look it up. But you basically construct this matrix and you try to figure out what the rank of the matrix is by either factorization, either by doing matrix factorization or by some sort of decomposition. There are many tools. It's not like there's only one way to do it. Many tools are available, but there are ways to do this, identifying whether they are linearly independent or not. Most of the practical problems, they are almost always linearly independent. So you don't have to worry about regularity, but the theory requires you to check for regularity. But real problems, almost every time, whatever problems I have worked on, everything is regular, so I don't have to worry about regularity. All right, so what is KKT? KKT theorem says X star is locally is a local minimum and regular implies there exists lambda star in Rm, mu star in Rr, such that. All right, so we have two sets of Lagrange multipliers now. One is lambda star, the other one is mu star. Lambda star corresponds to the equality constraint. So we'll call this Lagrange multipliers corresponding to the equality constraint, Lagrange multiplier corresponding to the inequality constraints, such that gradient fx star plus summation lambda I star gradient hi x star plus summation mu j star gradient gj x star equals to 0. Mu j star equals to 0 for all j in, not in, kx star. Mu j star is greater than equal to 0 for all j. Oh, I forgot to introduce another thing, the set of first order feasible variations. So let me do that here. V of x equals to d in Rn such that gradient hi x transpose t equals to 0. This is for all I.
What was it for?
This is first order feasible variations. First order feasible variations at x. And the fourth one is d transpose second derivative of f plus lambda transpose h plus mu transpose g Yes.
Is that non-empty for every regular point?
It will be non-empty for every regular point.
Oh.
Yeah. But it could be also, see, d equals to 0 always satisfies this condition.
Oh.
D equals to 0, d equals to 0. So,
Okay.
any other question? So going back to manifold suboptimization algorithm, whenever d was equal to 0, we dropped one of the constraints and started moving in some other direction. Remember? So yeah, it's always non-empty. Okay, so what does this KKT theorem says? KKT theorem is very similar to the Lagrange multiplier theorem. It says that instead of having one set of Lagrange multipliers, now we have two sets of inequalities, therefore two sets of Lagrange multiplier, lambda star and mu star. This first condition looks extremely similar to the Lagrange multiplier theorem. So nothing much to discuss here. These are the two new things that appeared because of the inequality constraint. In fact, if you look at it, these are Lagrange multipliers for inequality constraints, and they have to satisfy certain specific properties. So for each inequality constraint, the Lagrange multipliers have to be non-negative. And for inactive constraints, or constraints that are not active, the Lagrange multipliers have to be 0. Okay. So in fact, if you look at it, this one will be 0 for all the inactive constraints. So all you have to do is the sum over all the active constraints only. But because mu j star is 0, I'm writing it as sum over all the constraints. It doesn't matter. The other thing, that the fourth property is something that we have also seen for the Lagrange multiplier theorem. So second derivative of the Lagrangian, you pre-multiplied by d transpose, post-multiplied by d. It has to be greater than equal to 0 for all first order feasible variations at x star. So everything is very similar to the Lagrange multiplier theorem except for these two conditions that pops up because of the constraint. Okay. How do we prove this result? Let me just give you I'm not going to prove the result, but I'll give you the starting point of what the proof is. So this problem is similar to, or it's actually equivalent to this problem. Let me call this h tilde x. So gx less than equal to 0 is the same as saying that max of 0 comma gx is equal to 0. Okay. This is the only change I'm making. This is the only change I'm making. And what I'm claiming is that the two problems are equivalent. And then you apply Lagrange multiplier theorem. I mean, you go through the proof of Lagrange multiplier theorem on this particular optimization problem, and you end up proving this result. You end up proving this particular result. Any questions so far? Okay, let's try to solve a problem. I want to minimize x1 square plus x2 square x1 plus x2 is less than equal to or plus 3 less than equal to 0. My x is in R2. Okay, how do I solve it? So I need to define the Lagrangian L of x lambda mu, which is defined as f of x plus lambda transpose h of x plus mu transpose g of x. And this is the same as f of x plus summation I lambda I hi of x So let's compute the Lagrangian of this problem. Actually, there is no lambda, there is no equality constraint here, so I can remove it. Yes.
Do we always require it to be less than or equal to? Or
So if it is greater than equal to, you multiply it by a negative sign on both sides and it becomes less than equal to.
so in the multiplier, we would also use the negative instead of if it's greater.
Good question. So if it is, let's say my problem statement was this is greater than equal to 0. In this case, I will say that minus x1 minus x2 minus 3 less than equal to 0. Okay.
Yeah. So we would use mu times minus x1.
Minus that, yeah. Yeah. Okay, so I have this. So at mu star x star, the first condition needs to be satisfied. So I have gradient of x of Lx mu. This is equal to 2x1 plus mu 2x2 plus mu equals to 0. This means x1 star, this is at star, minus half mu star x2 star equals to minus half mu star. That's the first condition. How do I find the value of mu star? So if it was an equality constraint, all I will do is just substitute this x1 star, x2 star here, and I'll get the value of mu star. But now it's an inequality constraint. So what do I do?
We substitute the term for term three.
Sorry, can you say that again?
But now we know the dependence of x on the new terms.
Yes, we have a dependence of x on mu star. The real problem here is this is an inequality. If it was equality, it was easy. Life was easy. I would just substitute it here and I'll get the value of mu star. I have one equation, one unknown, easy. Now I have one inequality and one unknown. How do I solve one inequality with one unknown? That's the problem. Okay, so here is the way to solve it. I'm going to split the problem into two cases. Case mu star is equal to 0. So let's assume for the time being that mu star is equal to 0. What happens? I have x1 star plus x2 star plus 3 equals to 3, which is greater than 0. So the constraint is violated. Right? The constraint is violated. Therefore, mu star cannot be 0. This implies mu star cannot be 0 because otherwise I am violating the constraint. So the case is mu star is greater than 0. Remember, mu star was 0 when the constraint was inactive, right? So mu star equals to 0 for all constraints that are inactive. If I'm saying that mu star has to be strictly positive, it means that the constraints are going to be active. So I'll have minus half mu star plus 3 equals to 0. So remember, I was having less than equal to this condition violated, so I have to set it equal to 0 now. And what do I get the value of mu star as? 3. 3 is positive. 3 is positive, which satisfies this condition. So mu star has to be non-negative for all constraints. So whenever you are exposed to a problem where you have inequality constraint, the way to solve it is you first get all the x's in terms of Lagrange multiplier, and then for every possible inequality constraint, every Lagrange multiplier corresponding to inequality constraint, you have to set it equal to 0, not equal to 0, and then look for an appropriate combination under which you will get a solution that meets all of these different criteria. Okay. So if I had mu1 star and mu2 star, then I'll have case mu1 star equals to 0, mu2 star equals to 0, then mu1 star greater than 0, mu2 star equals to 0, then mu1 star equals to 0, mu2 star greater than 0, and so on. Okay, and I'll have multiple cases, and then I'll have to solve each of those cases and make sure that all the constraints are satisfied by the solution. And you will find a solution where all the constraints are satisfied, in which case that is a candidate for an optimal solution. Remember, this is a necessary condition. It assumes that x star is a local minimum and regular point. Only then these conditions hold. So it's a necessary condition, so this becomes a candidate for an optimal solution. Now we need to talk about sufficient condition, which is under what conditions can I ascertain that x star mu star pair is actually an optimal solution. Any questions so far on this example? Yeah.
So if that one is less than and or equal to 0, that means there's no optimal solution with the second case.
Yes, there will be no optimal solution in that case, but But remember, in the entire optimization that we are trying to solve in this class, we assume that the optimal solution is going to exist, right? But if you were going to MATLAB and you are building optimization solver for MATLAB, then you don't know upfront what the user is going to prompt, and you will have to figure out if it's a feasible solution, if it's a feasible optimization problem, not a feasible optimization problem, and so on. And many a times, you try to solve a problem in MATLAB and it will give you an error that this is not feasible. Or alternatively, in which case MATLAB is doing its check and saying that, look, your constraints are not feasible. You are saying that x has to be greater than equal to 0 and x has to be less than equal to -1, right? So it's an infeasible problem. So MATLAB will give you that error, or alternatively, MATLAB will say the solution is NaN or INF, in which case, there is no solution. Yes.
So, like, if you have more than one inequality constraint,
Yes.
do you have to check like all subsets of like the possible active
Yes.
constraints?
Yes.
So, like, if you have m, wouldn't that be like you have to check like 2 to the m?
That's right. Cases. You will have 2 raised to m cases here.
Is that like efficient to do that, or is
No. So that's why we'll study algorithms where you don't check for all of that. You converge to the optimal solution candidate optimal solution eventually. Right? So this is just for, let's say, examination where you will have one constraint and so you will do 2 cases and you will show something. But if you had, if you're talking about GE where they have like 1 million variables and 10 million possible inequality constraints, you're not really going to look at 2 raised to 10 million possibilities there. Any other question? Okay, so let's talk about sufficient conditions. Okay, so what's the difference between the necessary condition, the KKT theorem, and the sufficient condition? So KKT theorem is saying that the first derivative of Lagrangian is equal to 0. I have the same condition here. It's saying my mu j star is equal to 0 for all inactive constraint. Mu j bar is equal to 0 for all inactive constraints, so that's the same. Mu j star is greater than equal to 0 for all j. Mu bar j is greater than equal to 0 for all j. The one thing you don't see here, but you see here, is this constraint, that your Lagrange multiplier corresponding to the active inequality constraint must be positive. Okay, so you can't have a active constraint with 0, mu bar j equals to 0. So we'll look at an example like that, okay, and you will see why that is the case. And then the second derivative, d transpose the second derivative of Lagrangian d, has to be positive for all first order feasible variation that is not equal to 0. Then x bar is a strict local minimum. So in the previous example, we had mu star equals to 3. This was strictly positive for the active constraint, right? So we had the constraint was active in the previous example that we saw, and so that satisfies the sufficient condition. Also, the second derivative of Lagrangian was actually positive definite, so this is trivially satisfied for all positive definite matrices. Okay, so in the previous example that we just saw, all of these conditions were true, as a result of which I can conclude that x star in our case minus 3 over 2 is a strict local minimum. In fact, it's a global minimum because it's a convex problem. Let's look at an example where that sufficient condition would get violated. Anybody wants to cook up an example where the sufficient condition is violated based on the example we just did, while I'm erasing the board? I want to minimize x1 square plus x2 square such that x1 plus x2 less than equal to 0. What is the optimal solution for this? 0. So 0, 0. So this is the minimum value you can have. And of course, this constraint is active because 0 plus 0 equals to 0. So x star here is equal to 0. Mu star here is also equal to 0. For all active constraint, mu bar j should be greater than 0. That's not the case here. Mu star is equal to 0 here. So this is a situation where the sufficient condition is not satisfied. Okay, so that sufficient condition is not satisfied. This is still a convex problem, so this is still an optimal solution, but we are not using that sufficient condition to conclude optimality in this particular problem. Any questions so far? Okay, so when you go out in the world, when you are solving problems, most likely you will be solving a very high dimensional optimization problem. You will converge to a point x star, lambda star, mu star that satisfies all these conditions. The only way to know whether you have come to an optimal solution or not is to check for these conditions, in which case you can conclude that you are at a strict local minimum. If you happen to have a convex problem, then you are at a global minimum, so that's even better. On the other hand, if you are not verifying the sufficient condition, so whatever algorithm converts to, if you're not verifying these conditions are satisfied, all bets are off. Okay, we don't know whether we have converged to a point that is anything that is close to optimal or local minimum, or you cannot say anything about that because this is just a necessary condition for optimality. It requires X star to be a local minimum and regular. Then these conditions are being satisfied.
V of X bar, is it a finite set? Like set with
No, it's not a finite set. It's an infinite set.
Then checking for condition would be very hard.
It's very hard, for sure, unless you know for sure that this particular matrix is a positive definite matrix. If it is positive definite, then checking this is very easy because it's true trivially in all directions. If it is not positive definite, there are some ways to check it. It's there in the book, but we are not covering it in the class. What you essentially do is you augment the Lagrangian. So we'll talk about augmented Lagrangian method maybe like 2 weeks from now. And so we'll introduce this notion of augmented Lagrangian. So what you have to do is look at the augmented Lagrangian with some parameters sufficiently large, in which case if this becomes a positive definite matrix, then again you are in good shape. But in general, like you want the most general condition, I think it's very difficult. Any other question? Okay. So we have the same sensitivity theorem as well for inequality constraint problem. This is going to be used in your assignment 4. So X star is regular, X star, lambda star, mu star satisfy sufficient conditions Now consider this problem. I want to minimize f of x such that h of x equals to u, g of x less than equal to v. Then, and I'm going to call this p of u comma v, gradient u of p of 0 0 minus lambda star, gradient v of p 0 0 minus mu star. So you perturb the equality constraint a little bit, you perturb the inequality constraints a little bit. The optimal value, you take the gradient with respect to u, you get minus lambda star. You take the gradient with respect to v, you get minus mu star. So in the assignment, assignment 4, which is not due until 2 weeks, so you don't have to worry about it. But what you have to do is identify a situation where a supplier, a manufacturer has to outsource certain part of their production to a different company, and it turns out that that particular problem is equivalent to looking at the Lagrange multiplier and massaging it a little bit in order to figure out whether outsourcing it makes sense or doesn't make sense. Okay, so it's a very cool business problem. When my wife was doing MBA, she was assigned that homework and I liked it so much, I'm assigning it to you, and hopefully you will get some MBA level training through that particular assignment. So you have to look at the Lagrange multiplier, you have to look at the profit function, how exactly the profit is changing if they outsource it, and then you will have to figure out outsourcing makes sense or doesn't make sense. Okay, so that's all I have for today. Are there any questions? If there are no questions, either everyone understood everything or nobody understood anything. In any case, the videos will be on YouTube, so hopefully you will understand at some point of time. So thank you. Have a great weekend.